heat generation per unit volume. Rate of heat generation per unit volume and K is thermal conductivity is equals to, we have used yesterday, rho C by K into dt by dt. Am I correct? So this is the equation we need to remember when the cylindrical coordinates are given in the problem in case of solving heat conduction equation in 3D mode. Okay, and this equation I am highlighting it here. I'm highlighting it here for the sake of clarity. This need to be remembered. This we need to be remembered in future course. And in this, if it is in the absence of, heat generation, this term is going to be 0, and then three-dimensional heat conduction equation is going to be dou square T by dou R square plus 1 by R, dou T by dou R plus 1 by R square, dou square T by dou theta square plus dou square T by dou Z square is equal to rho C by K into dt by d. This equation we already talked in case of Cartesian coordination. This equation is given by Fourier, so this is called the Fourier equation. Okay, when again when it is asked to you, when there is a steady state heat transfer, means what? There is no change in the system, right, in the element with respect to time. There is no change in the temperature with respect to time is 0, there is negligible, then this term is also going to be 0, and this term, if it is available, heat generation is available, then this equation we call as a Poisson's equation, right? And in the absence of this also, in the absence of heat generation is also neglected. If then the equation is going to be dou square T by dou R square plus 1 by R dou T by dou R plus 1 by R square dou square T by dou theta square plus dou square T by dou Z square is equals to 0. And suppose in the case of one dimensional heat conduction in radial direction, direction is to be required to found, then the equation has become dou square T by dou R square plus 1 by R dou T by dou R is equals to 0 in case heat generation and the and it is steady state condition. Heat generation is negligible. Heat generation, sorry, here I'll rewrite it. In the case of heat generation, negligible, negligible, and and it is and it is steady state. Okay, so this is the equation, or I can write in a simplest form. This is equals to dou by dou r into r dou t by dou r. Okay, so this you can remember it. Okay, now next we'll go to the next topic, or some more information. I'll try to here give you some more. Suppose this equation can also be derived from the rectangular coordinates, from rectangular coordinates coordinates by by assuming what we have considered x and y and z, no. So rectangular coordinates as x and y and z. Therefore, by assuming x is equals to r cos theta, y is equals to r sin theta, and z is equals to z. Okay, so these are the equations we have derived and then concluded. Okay, now I'll go little ahead by taking the case of heat 3D heat conduction, 3D heat conduction in spherical coordinate system. Okay, so this I'll take the case now. In the third case, I'll derive this equation. Okay, spherical coordinate system. Okay, now for which again I will take a cylindrical coordinate, spherical coordinate in such a way, that I will show you the cylindrical spherical coordinate system here, like this. So first I will try to draw the x and y with respect to x and y Cartesian coordinates, how it is located. That okay. Now see, this I am taking as x-axis and this is y-axis. Sorry, and this is y-axis and this is z-axis. Okay, this is z, this is y, and this is x. Okay, now I will take an element here. I will take an element here like this. I'll okay, and the radius up to which is going to be R, and this is dr. Okay, and I will use another color to show you the dimension of the element. Okay, this is R, d theta is from here to here. Okay, and this one and this one and this one is R sin theta d phi, where d phi, how did you get this? D phi is nothing but to get the d phi. How did you get this? I'll show you how you have got it. Now this is the lines you are projecting lines. You are projecting it down. Okay, and here this is angle with respect to the other one. Sorry, this is d pi. The other one, this is pi, and this is d pi, and now this has been projected like this to get the r sin theta d phi. Okay, now this is description, means here the elemental volume we have considered is elemental elemental volume we we considered we considered as like v is equals to dr in one direction, and the other direction is r d theta, and other direction r sin theta d phi. Okay, this is v, elementary volume. Okay, now so entire picture I'll try to draw in the next diagram, because it is required to me the entire diagram, and draw in the next one. It is required to me. Therefore I'll write again here. The entire picture is here, something like in a bigger fashion. I'll write it here. uh, I'll write it right here. This is I've taken as r d theta, and this is dr dr. Okay, This is dr, and exactly behind of it, this is something like this one. Okay, so now I'll write it. This is d theta. This is dr. This is r sin theta d phi. Okay, okay. Now, to this element, to this element, let QR and Q theta and Q phi are the rates of heat transfer into the element in r theta and phi direction respectively. Direction respectively. Respectively. Okay. Now means I will show you the diagram how the directions it is entered into the system. Now I will take this color to show you, and I will take a small line to show you. See, in the direction of dr. Okay, now this is dr direction, means that this is dr, this is dr. Okay, similarly here also, if I see, if I draw a lines here, the behind view in a dotted line, it could have been like this. Okay, am I correct? Okay, now d in the direction of dr means this is the direction it is going. Therefore, I can say in this way, it's entering. This is QR. Okay, then to this QR, the area which is normal to this is this one. Okay, means what? The area which is normal to the direction of heat transfer is equals to r d theta into r sin theta d phi. Okay, right. Now similarly, when I take after this elemental dr, then it is going to be up the heat rate at which it is coming out of the system in r direction is equals to q r plus dr. Okay, If you are thorough, then I'll go to the next direction. Okay, now other direction. Now R is over. Now theta, I'll talk about theta. In case of theta, this is theta direction. Okay, this theta direction means that this is R d theta. This is also R d theta. Okay, right? So now it is entering in this direction. Let's take this entering in this direction. Theta. Okay, this is Q theta, and it is leaving in this direction. Then it is going to be Q theta plus d theta. Okay, right? And the other direction, Q, or that is phi direction. So phi direction is, this one is r sin phi, r sin theta d phi, and this is also r sin phi d phi. Okay, this is also r sin phi d phi. Therefore, it is radially enters here and it goes out like this. Therefore it comes like this. You come here. This is equal to Q phi, and it comes from this side, the other side. This side is Q phi plus d phi. Okay. Now, so now I will try to summarize and minimize my explanation. Why? Because already we have taken enough uh, introduction about these cases. Now, net, sorry, next I will write the total heat conducted into the system. I'll write here the total heat rate conducted into the elemental volume V is equals to QR plus Q theta plus Q phi. Okay, so that is, we know the equation of heat conduction. This is equals to minus K into area normal to this R direction, QR. The area normal to the R direction is simply R d theta, R sin theta d phi, or d theta into R sin theta d phi into dou t by dou R. Okay, plus area, the heat conducted into the element in the direction of theta. it is shown here, theta, it is shown here. Okay, this it is written as, I will make use of square brackets here. Okay, then here also I will use a square bracket minus k into normal area, normal to the direction of q theta. The area normal to the direction of q theta is, this is dr, and again this is this one. Okay, this one r sin theta d phi. Therefore dr into r sin theta d phi into dou t by, the length of this is, theta direction is r d theta. Therefore dou t by dou l, dou t by dou x, you know the gradient is. Therefore I will write it here, r dou theta. Okay, now plus I will be using minus, again square bracket, minus k into, and phi direction. Phi, di phi direction, if you see the phi direction, sorry, I should use the arrow. This arrow is, I should use this arrow as d phi direction, right? This is the direction. Okay, sorry, I have, this is this way. Okay, now in this direction. So this is equals to, I'll write it here, k into the area which is normal to this, this phi direction is going to be, what is the area which is normal to this is, this is d theta, and the area which is normal to this is one dr. Okay, therefore dr into r d theta. Are you following? See here, this is the area which is this one. Okay, right, now into dou t by, and what is the direction it is, what is the length of this one, is going to be sin r sin theta d phi. Therefore dou t by r sin theta dou phi, r sin theta dou phi. Okay, clear? So this is the case in which is heat rates which is enter into the elemental element. And then the similarly the total heat rates conducted out of the elemental volume V could have been, I will write first, this is equals to Q R plus dr plus Q theta plus d theta plus q phi plus d phi. Okay, right? Now I'll go to the next slide. This is equals to, according to Taylor series, I will write first expansion. According to Taylor series of approximation, according to Taylor's series of approximation q r plus dr is equals to, I can write it as qr plus dou by dou r of qr dr. The same way, q theta plus d theta is equals to, I can write as q theta plus dou by dou theta of q theta into dou by dou theta, because here theta is r d theta or dou theta into r d theta. Okay, now the same way I can write it here, q phi plus d phi is equals to q phi plus dou by, here what I used, r sin theta dou phi into q phi into r sin theta d phi. Am I correct? So this is according to the Taylor series of approximation. So now already I mentioned what is that, in this case I have mentioned total heat rates conducted into it. Okay, now I will write the summation of these two are simply, now one more case I will write it. Now the net heat conducted into the elemental volume is, I can write it as, that is equals to, I denote as the net heat, I can write it as q net is equals to, we know heat added into the system as positive, heat taken out from the system, heat ejected from the system as negative. Therefore I'll write q r plus q theta plus q phi minus q r plus dr plus q theta plus d theta plus q phi plus d phi. Okay, that is equals to, already it is there, so qr and this qr get cancelled, and q theta plus q theta gets cancelled, this and this also gets cancelled. Therefore you will be left with dou by dou r of qr dr minus dou by r dou theta of q theta into r d theta. Am I correct? Plus, sorry, this is not plus. This is minus dou by r sin theta dou phi into q of q phi dou by r sin theta d phi of q phi and r sin theta and d phi. Okay, right? Now, okay. Okay. Now, next I'll go to next slide. Now, so first step by step I'll write it here in this fashion. How it is written. Okay. First, Q net is equals to Q net is equals to minus, I'll take a big bracket, is it dou by dou r into qr is there, therefore dou by dou r into qr is nothing but minus k into r d theta into r sin theta d phi into dou t by dou r dou t by dou r of dr. Okay, next again other one is minus dou by r dou theta into dou by dou r of dou theta into minus k dr into r sin theta d phi into dou t by dou theta into r d theta. Okay, minus dou by r sin theta dou phi of r sin theta dou phi of this is equals to minus k this is equals to minus k minus k into normal to the is that phi direction is equals to dr r d theta into dou t by r sin theta r sin theta dou phi r sin theta dou phi into r r sin theta d phi. Sorry, okay. This is the bracket which is ends here. Okay. Now that is equals to, I'll write it here from here. I'll start from here. That is equals to see here k is there, here k is there, here k is there, and minus is there, minus is minus plus, this minus to minus plus minus to minus plus. Therefore I can write k out. I will take k out here. I'm taking k out here, and then I'll rewrite that equation as like this: dou by dou r. Please follow me. Dou by dou r into here. See, r is there, r is there. I'll write it as r square, and dou t by dou r. I'll keep it as it is. Dou t by dou r as it is. Okay, and the rest of the things like d theta, r sin theta, d theta, r is r I have taken, therefore d theta sin theta d phi I will take it out, therefore, and I'll write it as, and again dr is also there, so this is all I take, d theta sin theta and dr I'll take it as, okay, d theta, okay, uh, r is not there, and dr and sin theta d phi I have taken out. See, you can see here r I have taken out, so d theta remain, d theta I kept it, dr is there, dr I kept as it is, and sin theta, r I have taken out, therefore here r it is here, therefore sin theta d phi. Now plus next I'll take this one, dou by r dou theta into, see here I'll put sin theta here inside sin theta, okay, sin theta, and again dou t by r dou theta inside, okay, this I kept it here, and dou t by r dou theta I kept it here, therefore dr is coming out, dr has come out, and r I have not taken, therefore r is also coming out, r, and again d theta is there, so d theta is there only, okay. Now, okay, So here dou by dou r theta sin theta I kept dou t by r d theta dr I have taken here. R is there, r I have taken here, and r d theta is there. R is there. So r, and again what else is there? d phi. D phi. Okay, clear. Then plus dou by r sin theta into dou by r sin theta into dou psi, sorry, dou phi of, I will be using, see here, I will be using dou t by, I'm not taking anything inside into the bracket, dou t by r sin theta dou phi. So dr is going out, dr r d theta is also comes out into r sin theta d phi. Okay, right? So this is, I have simplified. I am going to further simplify it like this. I'll write it here. This is equals to, this is equals to k into k r. I will take 1 by r square as common into dou by dou r into, I am keeping r square as it is, dou t by dou r, okay, plus here r into r square, therefore 1 by r square, 1 by r square, right, 1 by r square sin, see here, this one, 1 by r square, second one, 1 by r square, what is this? Second equation, sorry, first 1 by r square, r square sin theta, 1 by r square sin theta, I am taking out here 1 by r square sin theta, I will take it out and I will put here sin theta into dou t by dou theta. Okay, means here I have taken r sin theta divided this equation divided by sin theta. Therefore, if I use here divided by sin theta, it is keeping as it is, and here one sin theta will come. Here I have divided in this equation r square. Therefore, here r square will be coming. Okay, you keep in mind. Okay, here r square and d theta, or I can say r d theta, r sin theta d phi, and dr is there. Here sin theta is missing. To insert here sin theta, I have taken here sin theta here. Therefore, it will be this sin theta and this sin theta is gets cancelled. Therefore, I will use here sin theta, and I am keeping here sin theta. Okay, so like this sin theta, then sin theta plus 1 by here r square, r square, r into r square, and sin theta into sin theta, sin square theta, and dou by dou phi of, what is remained here, dou t by dou theta, dou t by dou phi, sorry, dou t by dou phi Okay, already I have taken everything, right? Dou t by dou phi into, this is what is it, dr into r d theta r sin theta d phi. Therefore, into, now this r square is not there. Now r square, since I have used here r square, therefore here r square is coming. Therefore r square d theta dr sin theta d phi, which is common to all the cases. So here r square is not there in this. In here, if you compare this one with this one, r square is there. Therefore, I have divided this by r square, and therefore here r square is coming. And here sin theta is not there, so I have put here sin theta as the denominator. Therefore, here sin theta is coming. Therefore, the equation is balancing. Here, nothing is there. Therefore, this I can use as, in place of this, I can use elemental volume V, right? Initially I have used there. Okay, means the equation is coming out to be k into 1 by r square dou by dou r of r square dou t by dou r plus 1 by r square sin theta into sin theta into dou t by dou theta plus 1 by r square sin square theta, okay, into dou by dou phi of dou t by dou phi into elemental volume V. Okay, right. So this I denote as equation number 1. And according to my the, introduction to basic equations for three-dimensional heat conduction in case of a Cartesian coordinates, I have denoted this one as this one as 1. Okay, so this I am denoting as 1. Now next, I'll go to next slide. Okay, I am going to the next slide. Okay, the next slide is what I mentioned is nothing but, so now I'll, before going to it, I'll try to define the first law of thermodynamics. First law of thermodynamics, which was already defined. Thermodynamics, that is, if there are heat transfers into and out of the system, that is equals to, therefore the summation of heat transfers is equals to change in internal energy. Summation of heat transfers, summation of work transfers, or change in internal energy. If work transfer is there, or simply I will write delta Q by delta T is equals to delta E by delta T. This is the summary for in case of a solids, which we already defined. Therefore, this is delta Q by D is equals to nothing but this is net heat transfer. Q net. Okay, Q net plus, because of that heat transfer, as well as there is a internal heat generation because of the heat transfer. If something is happened inside the, then there is heat generation. This is equal to Q, we call it Q into V is equals to change in internal energy dou E by dou T, which we have defined. Now I'll write. So this is first one, this is second one, and this is third one. Okay, now I'll take second case. This I'll take into upon. Therefore, the second, what it talks about, it is, let Q dot be the heat generation generation per unit volume rate within the element within the element. Therefore, total heat generation will come to Q into what is the volume it is? The volume is R d theta and dr and R sin theta d phi. Okay, so this is equation number 2. Okay, now next number 3. This I will tell you. We know change in internal energy from thermodynamics is mc dt, where m is equals to mass and c is equals to specific heat and dt is equals to temperature difference. And this unit you are going to get mass is in kg and this is kg per this is equal to kg specific heat kg per kilojoule per, sorry, this is kg, this is kilojoule per kg Kelvin and Kelvin. So the Kelvin gets cancelled, gets kg gets cancelled, only the left with is this is kilojoules. Okay, but if I want to calculate here the change in internal energy from thermodynamics, we know it. Now we require the change in rate of change in internal energy, right? Therefore, rate of change of internal energy can be rate of change of internal energy can be calculated if we take m dot is nothing but mass flow rate, that is mass flow rate m as m dot, that is mass flow rate in the equation. Therefore, now m dot can be written as, density into volume, density flow rate into volume. This is equal to volume is in our case dr or d theta, okay, or sin theta d phi into c into dt by dt. Okay, here if we take in the equation m dot into c dt, you will get a rate of change of heat energy, or else what I can do, I will put m as it is and c and rate of change of temperature, I will take it here. Rate of change of temperature I have taken here, right? This is equal to, you will get that rate of change of internal energy. So this is the third equation. Either you put m by time or dt by time. It comes to be rate of change of internal energy. Okay. Now combining all these equations, now I'll combine 1, 2, 3. I combine 1, 2, 3. I'll write one by one. Okay. Combining all equations, that is equals to k into 1 by r square dou by dou r into r square dou t by dou r plus 1 by r square sin theta dou by dou theta of sin theta into dou t by dou theta plus 1 by r square sin square theta dou by dou phi of dou t by dou phi into r d theta r square, which I mentioned here. I'll write r d theta r sin theta d phi into dr plus then q dot into volume is written as r d theta into r sin theta d phi into dr is equals to rho, it is not rho c into sorry rho, rho c into volume is r d theta dr r sin theta d phi into dt by dt. So in all the cases, r d theta r sin theta d phi dr and again r d theta r sin theta d phi r gets cancelled. Then the equation will become k into 1 by sorry r square, okay, k into 1 by r square dou by dou r into r square dou t by dou r plus 1 by r square sin theta dou by dou theta of sin theta d theta sin theta dou t by dou theta plus 1 by r square sin square theta into dou by dou phi of dou t by dou phi plus q dot is equals to rho c dt by dt. If k goes from here to divide, if I take by divide the entire equation by k divided by k, then this will become the k cancels here, k will come here, k will come. And this equation can be written as 1 by alpha into dt by dt. This alpha is called thermal diffusivity. Okay, right. Now, okay, this equation, only this equation I'll try to explain to you once again. This equation I'll try to write it. Okay, this I can use. This is uh, it is u and v, d by dx of uv. It can be written as u dv plus v dv. Therefore, I can write it as 1 by, that only I'll write it 1 by r square into u, therefore r square into dou square t by dou r square, so r square gets cancelled, plus 1 by r square into integration of or differentiation of r square is 2r dou t remains same, dou t by dou r. That means this r gets cancelled, therefore this is equals to, I can write it as dou square t by dou r square plus 2 by r dou t by dou r. I can write this one in place of this equation. Okay, right? So if in case of one dimensional heat conduction of a spherical sphere in radial direction will become this one dou square t by dou r square into 2 by r. If in the absence of heat generation this is equal to 0 and it is a steady state, this is equal to 0, that is therefore this is equal to 0. This is called as the one dimensional heat conduction equation of a sphere in radial direction. This equation is called as, okay. So I'll stop it here. When we come back to the class, I will try to summarize. I will try to summarize. I'll take one more slide. When we come back to the class, next class, okay, I will discuss summary of 5 classes which we have taken till now, okay, and then we will be discussing initial and final initial boundary and final boundary conditions for various cases, and we'll go to one dimensional one dimensional steady state heat conduction cases. Steady heat conductions will take up, okay, heat conduction will take up. So I advise you, please be seated at your places with one calculator, notebook, and also with data book when whenever we require to take properties of materials to solve some problems. Okay, right? So means when we come to the next class, we will be summarizing. When we come to the class, we will be summarizing the five classes what we have considered so far, and we will be discuss initial and final boundary conditions for the cases whatever we have studied for this past five classes, and then we'll take up, if time permits, we'll take up one dimensional steady state heat conduction equations and we solve the problems. Okay, for which we require a calculator, notebook, a data book. I'll already told you in the first class that a data book written by Dom Kundwar is enough to me to solve some of the problems. Okay, right? So I will sign out now, and I'm expecting you are coming to the classes with the items like calculator, notebook, and data book, and you try to note down the summary of five classes. I'll be giving in a brief manner with a PPT instead of writing on the board. I will try to give you a PPT form so that you can able to analyze whatever we have studied so far in a brief manner. Maybe one or two slides will be helpful to you in solve the problems in coming classes. Okay, thank you.